Okay, welcome everyone, and good morning. Do we have, I guess we have, I'll just say we have Sonny Gallant subbing in for Robert Henderson today. Steve? Do we have someone for the adoption of the agenda?
So moved.
Thank you, Darlene. And with that, we'll jump over to our guest today. Welcome. And if you could introduce yourself, that would be great. And
I will. Okay. Good morning, everybody. Thank you so much for.
it's if you sit down,
Okay.
you don't have to stand up.
Okay, that's
and
great.
just for the mic, so the mic will catch you there.
Thank you.
No, that's fine.
So, thank you so much for inviting me to share with you my knowledge about hydrology in PEI. First, I would like to introduce myself a little bit. And I work for the PEI Department of Environment years ago. I started my job there as a hydrogeologist in 2002. I worked for them for 8 years. And I did groundwater monitoring, assessment, and modeling in PEI. And to support and groundwater allocation and a lot of the water permit. In 2011, I moved to work with Agriculture Canada as a senior hydrogeologist. A year later, I was reclassified as a research scientist. So from then to now, I have been doing agriculture groundwater quality research with them for almost 10 years now. So my current program focuses on agriculture impacts on water quality. So today, I'm going to share with you some of the knowledge about PEI hydrology. And when I received your questions in the letter, and I did a little bit of research about why I was invited here. So I found the context. So I decided to answer your questions in the context of PEI hydraulic cycling. And so my presentation will be a little bit longer than a few minutes, because answering those questions, two questions will be taking about a few minutes. So the title I'm presenting is, and how does stream flow respond to groundwater pumping in PEI specifically? And I will touch on a few sub-items here. I want to show you some basic facts of groundwater in PEI that will set the context. And I will answer your questions directly, recharge, confined and unconfined aquifers. And then I will show you and how stream flow responds to constant pumping of groundwater and to a seasonal pumping. And then I will give you my some conclusion remarks. And here are some basic facts about PEI groundwater. And this makes it unique. PEI is a unique place. And PEI is completely dependent on groundwater. Is completely underlined by one aquifer. It's sandstone aquifer. It's from the west tip to the east tip. It's the same similar geologic formation, and that provides house to the groundwater. And the aquifer provided all the drinking water and a large majority of industry water supplies. And groundwater discharge contribute to over 65% of stream flow. In the summer, almost to 100%. And increased demand of groundwater raises concerns of aquifer depletion or aquatic habitat damage. So whether groundwater should be granted for irrigation is a live debate. So look at all these facts together, you will find that it's a unique situation. So we have to look at it locally rather than bring the knowledge from other places. And here is a diagram to show you a watershed. And then watershed basically is a physical drain area and has a boundary. The water will, there's a divider, the water will drain into the lower places. And in this watershed, you will see that precipitation landing in the surface. At the same time, there will be evaporation too from the soil surface and transpiration from the plant. So actually, it's pretty hard to separate the transpiration and evaporation, so we call it evapotranspiration together. So the precipitation when landed to the ground, and there's another component. It's going to, if the soil is saturated, and you will create a runoff. The runoff will be the overlaying runoff. It's going to get into the rivers. And there's another component. That's infiltration. That infiltration is going to seal into the soil, and then to the unsaturated zone, and then to the water table getting into the aquifer. So the water that infiltrate from the land surface and percolate through the unsaturated zone and reach the water table, that's the recharge. That's the recharge. So you have rainfall, evaporation, transpiration, and runoff and recharge. That's the end product of your infiltration. So once the water gets into the aquifer, normally it not move vertically anymore, and it normally is more horizontally moving because the bottom has an impermeable bottom there, and then it's push it. It will not let it go any further. Will not let go to the other side of the earth. So that's how it works. So I put the definition of recharge there. I'm going to read it to you. And water percolate down through the unsaturated zone and into the dynamic groundwater flow system, contribute to repletion of the aquifer. It's like in your bank, you have a saving account, and you have your income coming in. That income is your recharge. And confined and unconfined aquifer. This is a diagram to show you a profile, a geological profile. That profile has two aquifers there. One is the confined aquifer, the other one is the confined aquifer. The confined aquifer is the one that on the bottom, and we call it confined because there's a confined layer on top of it. That confined layer will not let the water go through, so the contamination couldn't go through either. So that confining layer, actually there's another name, we call it aquifer. And then on top of that is the unconfined aquifer. The unconfined aquifer is open to the air, to the soil. So that's where the recharge coming in. Okay, you see the water table there? And so the confined aquifer also receive recharge too, but from a little bit far away, from the outside the confined layer. But if the water coming from the unconfined aquifer, and if you want that water to get into the confined aquifer, you have to go through the confined layer, which will not permeable, will not happen. So you see that if you punch a well into the confined aquifer, and the water will pop it up above the confined layer, and depends on the pressure on the confined aquifer. If it's higher pressure, it's going to be popped up higher, and you can have a artesian well too. If the pressure is really high, you can really shoot it out of the ground surface. So that's the confined unconfined aquifer. Okay, I want you to guess what's the aquifer in PI? Confined, unconfined. Make a guess. Okay. So the PI aquifer is a little bit different. It's a semi-confined. Okay. So what happened is we have this bedrock is layered. So the water normally is storage moving through the interbed fractures. So the sandstone rock the water will not go through. But there's fractures somewhere. So the water from the top, from the soil, will go through there and find the way through the fracture and get into the other fracture. So it's a fracture network comprise this fracture network. So in some section, it's confined because that rock is continuously. But at the end, you're going to see a fracture, so the water is going through. So it's semi-confined. Okay? So this is a picture. I got it from Suri on my research site. You can see that the well hit a confined layer and hit through the confined layer. The water shoot up. So the water table is higher than the ground surface because the confined layer pushed the water there, has a lot of pressure. So you can see the water coming out. And this is quite common in PI actually. And there's another one, Clark Creek. It's in Highway 20, and you will see that right beside the creek, the water is shooting out. So it's quite common. In the PEI aquifer stream system, and there's about almost 200, over 200 watersheds in PEI. Even it's a small area, but it has a lot of watersheds. They're tiny. And the biggest one is about 200 square kilometers. And then below the ground surface, there's the formation. It's about 1,000 or 1,600 meters thick. But the water only housed in the top 100 or 200 meters area, because if you go deeper, the pressure is bigger, because you have the land surface loading, and the fracture will be very tight, so the water will not go through anymore. So the water only on the top, about 150 or 200 meters. The most productive is the shallow part, because you have less pressure and bigger pressures, and storage more. Okay? And that's a picture I took from the Cavendish Beach. You see that the water seeped out of springs when the tide is low. And you can see those multiple springs coming out. That's all groundwater discharge. So you're asking me to recharge, and then the water has discharge. So it circulates dynamic. And then if you zoom in, you see that this is the rock, and then the spring bubbled out. So that's on the beach. But in our creek, in our rivers, it's similar ideas. The spring will seep it out at a lower place. The water recharges in the higher place and migrate under gravity and to the valley and seep out a spring, and the beach and seep out a spring too. So they come from the higher place and discharge in the lower place. That's how you circulate it. And it only happens from ground surface to about 200 meters deep. If you go deeper, it's pretty tight. The flow is very weak. Okay. The dynamic part, and then it's on the shallow part. And okay, look at the quantities. And in PEI on average, and you'll receive about 1,100 melt precipitation. This precipitation breaks down in multiple components. And the evapotranspiration, it's about 40% of that. It's 440 melt. And the recharge, it's about 40% too. It's about 400 or 440 melt. Depends on the year. In the dry year, you have less of that. In the wet year, you have more than that. But that's an average number. And about 20% of that begin runoff. And then the breakdown in each month, on the right-hand side, the up corner, is the breakdown of the multiple components. You get precipitation, evapotranspiration, and drainage. That drainage is basically the recharge. You see that, the monthly distribution. Okay? And the evapotranspiration, there's a lot in May, and June, July, in the growing season. And the recharge is very little in those seasons. Do you know why? It's because most of the water loses into the air. And recharge only happens in the fall, spring, and winter. In the summer, you have very little. Okay? You got to remember this one. This is very important. So it's like in PEI, a lot of people work in seasonally. You only have income in the season. You don't have income in another season. You got to store some money in saving account in order to survive. Similar idea in our aquifer here. And then, well, I show you this diagram. It shows you the water table, and then the stream flow, and the groundwater component in the stream flow. That's the blue line. So you can see that they basically it's from Blooming Field in almost to getting close to Tignish in that area. We have a long-term well there, and there's a long-term gauging station there. So you show the flow. You can see those three things correlated really well. And in the fall and spring and winter, you have a lot of runoff, and then you have higher recharge, and you have higher groundwater into your stream too. You see the cycle in there? But the key point I want to show you is there's no long-term declining or long-term going up. So basically, in the long term, it's balanced. Income and outcomes balance. If you see a declining, you're in trouble. Basically, that means the aquifer is depleted. We don't happen, that doesn't happen here, but it happens in many places in the world. Many places. From the country where I came from, there's a big problem over there. So if this aquifer, under the natural condition, you have recharge and discharge into the river. But if you pump groundwater, and then you know what's going to happen. You're going to intercept part of water supposed to go into the river. So you reduce the stream flow. Okay? But the thing is, so you want to know how much influence you have, so we can do a pumping test. We drill a well there, we pump it for a little while, and we can measure how much flow reduction in the river. But if you want to see a whole watershed impacts on the stream, you need about, say, 20 wells. It's very expensive. You need to maybe pump about a month or 2 months to figure that out in order to get a full-scale pictures. But that's not very economically viable. So normally we build a model. That model, based on the short-term pumping test data, calibrated, and then we use the model to predict the long-term and larger-scale impacts. That saves money. And the model, actually, I'm a modeler, actually, so I trust the model, and then it's physics-based. Okay, so that's the, next I want to show you the effects, the real effects in the Winter River Basin, some data. And that's the pump in 3 well fields, Unit, Brackley, and then Suffolk. And then it increased a little bit. You see the line over there? Probably about almost 1% increase every year in this period, 1990 to 2010. But now currently, this number is a little bit older, but currently they adjust the distribution of pumping from the 3 well field. I think they pump more in Suffolk and reduce in Brackley to reduce the influence on the river. So that's the older number. You see that they pump 1,000 gallons in Brackley, a little bit over 1,000 in Unit, and 800 in Suffolk. And you can see that the base flow reductions are almost 100% in Brackley. And you use about 108% of recharge. You basically taking water from outside your watershed. Okay. So when we talk about that, we only use 1 or 2% of water in PEI recharge. That's on the island wide average, but on this local watershed, that's not true. Okay, that's island-wide sounds okay, but locally has an issue still. Okay, let me give you an example for you to understand this. In PEI, we say, okay, our household income is $50,000. We're good. But actually, some family only got about $20,000. So you have to look at those problems. Okay? This is critical, I think. And the impacts on the Winter River, you can see that I basically plotted the flow in 3 rivers, Winter River, Wilmot, and West River. You can see the red line, the black line, they almost lined up together. What does that mean? Even those 2 watersheds are far away, they produce similar flow rate. But the Winter River is below those 2 lines. I'm thinking the Winter River, if you don't pump, the three lines will be together. But now you pump and then you reduce the flow. This is why the line below the other 2. Okay, that's the amount of impact you have. Okay, but even though the Winter River Basin has some flow impacts there, but you don't see groundwater level decline over time. Do you know why? It's simply because you reduce the flow, the flow is supposed to get into the river. So you take part of it, but it's still balanced. Do you know what I mean? You take part of the flow in the river as human use, but the recharge and the discharge are still balanced. So there's a new balance going on there. Once you balance, you're not going to see the water level decline over time. You're not depleting the aquifer yet. But if you pump more than the recharge, you're going to see the line going like this way. But we are not there yet. So even though you pump, you have a lot of impact, you don't see the declining. But because it's not depleting the aquifer, you're stealing the water from the river. I hope you get this, but if you don't, ask me, okay? And then the other one, potential impacts in the Wilmot, because it not happened yet, but I'm going to use the model to demonstrate you that impact. This is a seasonal pumping. In the Winter River, it's 724 pumping. And here is a little different. Let's assume that it's pumping in the summer for irrigation. Okay, that's an assumption. Okay, so that's the watershed I have here is the Wilmot watershed. And in order to model that, I cut the big watershed in so many small cells. because if you treat the watershed as a whole unit, it's too coarse. So you cut it in small shells, and you can simulate a more high resolution, refined results in local basis. So I define it, and then I build a model, I calibrate it. I hope the model can reproduce the reality, the water table, the base flow, in the same way we observe in the river. So that I have faith on it. So that's the calibration results. They agree with each other really well. Okay? And then I make assumption. Okay, let's say everybody pump groundwater for irrigation in the watershed, and then in the dry year they have used 10 inches of water, and then in the wet year they only use 5 inches. So let's try that in the model and see what happens in the flow. I'm going to show you those scenarios. Okay? And that's the curve look like. So what I did is I simulated 2 years, 2000 and 2001. Why did I pick 2001? Because that's a historical dry year. And then I check those pumping scenarios and see what happened if that didn't happen again, if that 2001 dry year happened again. So that's what happened here. The blue line or the green line is the natural condition. Nobody bothered. Okay? Oh, that's the 5-inch water 5-inch water pumping scenario. You reduce the flow by 20%. And then the red line is a 10-inch water application. You reduce the stream flow by 40%. Okay? Okay, I put these two together, the Winter River and the Wilma River together, and do a comparison. Okay. In the Winter River, you pump a little bit over 3,000 gallons a minute, and that almost 40% of recharge, and you reduce the stream flow by 37% in the very dry year, dry season. And in the Wilma, if you pump 5-inch water, and that's about 3,500 gallons a minute, that corresponding, because that's only a short period of time, only in the growing season. Do you know what I mean? And then it's end up only about 7% of recharge. But the impacts is 20% reduction in the stream flow in the dry year of the dry season. But if this year, the 2020, this COVID year happen, the dry year, you're gonna end up seeing 40% reduction. That's likely happen. So, well, I think you have better sense what happened now. When you're talking about, okay, I give you a diagram to show you here. The problem, where's the problem? And let's say this tank is the aquifer in the Walmart. So in the fall and winter and spring, there's a lot of recharge. The aquifer water table is high, and the discharge into the river is okay. But now, in the summer, and this aquifer is going to be lower water because, like I said before, there's very little recharge. But the discharge in the river is 27 every day, every minute. So it's going to deplete your water. It's like you're accounting. If you don't have income, you use it. You're going to make up a red account. Similar idea. But still, because nobody pumping, nobody competing water for the stream discharge, it sounds okay. But if you put another scenario, you pump in the summer. If you don't pump the right amount, you pump a lot, you potentially bring the water to a low level, and then you bring the stream flow low. So that's just an impact there. Zero impact, if you pump, you want to see zero impact, it's impossible. It's just a matter of time. It's just a matter of where you pump it. So what level of impacts you can live with, that's, you make the decision here. So the problem here is we have a lot of water, but the water normally comes in the season that nobody wants water. But in the season you want water, there's very little storage in the aquifer. Do you know what I mean? So the problem is a temporal disparity between high recharge and high water demand. So we got to juggle with this. If we can storage all the spring snow melt there, we are going to be great. All right, so I hope that, okay, I'm getting to the end now. PEI's groundwater is renewable. It's vulnerable to contamination because it's semi-confined. There's no confined layer, it's semi-confined. The contamination can get into it, okay? And the recharge is abundant. And overall groundwater extraction are low on an annual basis, but in a seasonal basis, it create problems. I demonstrate that. Okay, and then on the island wide, its use rate is low, but on a local basis, it has some issues there. Okay, so you have local and seasonal issue. That's what we need to manage. So how much stream flow can be perturbated? No, that's you should answer that. So how do we know the physical impact? I believe if you want to do a full-scale testing, it's very expensive. It's invisible. You gotta believe doing the modeling. And the modeling I'm talking about here today, it's not just we are using that. And it's a global standard. It's basically in the United States, in Europe, and all the places for this large scale and long-term assessment, you gotta use this model. And we are very lucky in PEI to use the model because our geological formation is quite uniform. So we don't have to spend a lot of money to figure out what the geology look like to feed the model before we can use the model. So we are quite lucky but that way. Okay, thank you. With that, I conclude my talk and then be ready to answer your questions.
Thank you very much. Lynn?
Thank you, Chair. Thank you for your presentation. This was really technical, and I hope we can have an opportunity to look at the slide deck afterwards, if that's possible. That would be fantastic. Yes, I really want to go through this again, but there's a few points that you made that I would just like to talk through, if that's okay. It sounds to me like even though we know what contributes to recharge, how much recharge we have in any given year is highly variable. Is that a fair statement?
Yes.
Am I correct in saying that calculating groundwater recharge is complicated and more averaging and estimates than precise?
Correct. And measuring groundwater recharge is challenging. How to determine that number? And there's multiple ways to do it. And to use a water balance approach. And different people may create a little bit different numbers. And different years may be different too. And different watershed may be different too. So another way to calculate it is the monitoring the stream flow. So once because that's the water is coming out from that watershed. So then you use the output to judge, to infer what's the input. So so I will say that recharge is semi measurement because you know how much is coming out in the outlet of watershed. So because we have at least 7 or 8 gauging stations in PEI, and historically there's more, and they terminated because there's no money to continue those ones. So even though they terminated those ones, and the numbers still okay because they have 5-6 year numbers. So you're right. So I did some research on the recharge in PEI, and I found that a few numbers. And in the 1980, a scientist called Ray Francis, and he was the provincial hydrogeologist. He got some numbers, and also found some numbers from NRCan, Natural Resource Canada, and my own numbers, and George Summers and current hydrogeology. We put all those numbers together, and we agreed that it's variable, but we have certain confidence that the numbers are in that range. So I would say that in the central part of the island have more data, and we have more confidence numbers. It's about 440, and in the low year it could be 380, and high year it could be 550. And so on the west part of the island, maybe a little bit lower because the formation has more clay stone over there. And for the eastern part of the island, the number will be somewhere in between. So there's a little bit of regional difference and annual difference, and also method dependence too.
Lynn?
Thank you, Chair. So you sort of spoke to my next question. I wanted to talk about the regional differences or the differences by watershed. I know we say we have about a 40% recharge rate. I think that's about what you had estimated, but I'm curious how that breaks down. I know the western part of the island could be drier, for example. Would they be prone to seeing lower or higher rates of recharge?
that number, the number I presented based on the central part of the island. So on the west part of the island, I did a work in 2004, and I found out that that recharge was slightly lower than the central part of the island. But it's not far away. But for example, in the central part, it's 440. Over there, maybe 420. It's not far away. But the thing over there was the temporary distribution is a little bit different. And in the spring, it has higher stream flow, and it had lower flow in the summer compared to the eastern part, to the middle part of the island. So the temporal distribution of the base flow and the recharge is slightly different than the central part. But so if you're interested in those differences, probably there's some difference there, yeah, because the geology difference.
Lynn?
Thank you, Chair. This is very interesting to me, and I want to make sure I have a good understanding of it. So forgive me if some of these questions are a bit redundant. I just want to make sure I have a clear picture of this. You had indicated that the province has one aquifer. Is that an...
Well, it's partially true. When I say that one aquifer, is the whole geological formation is similar. But if you are talking about aquifer, and we normally manage that on a watershed basis. So if every watershed has its own aquifer, but all those, say watershed A and B, they are neighboring, the aquifer is connected. So then it's basically a simple aquifer. If you pump in aquifer in watershed A, if you pump a lot, you're gonna influence your watershed B, because they are so close. And the watershed divide is a surface watershed divide. The groundwater, there's no divide there. Okay, so actually I have a picture right here. I want to show you this one, and this is the Brackley and Unit and Suffolk watershed, and Wellview, and plus the Close Creek, and those lines, those brown lines, is the flow line, and the watershed boundary for the Close Creek is the green one. It's the green color over there, and actually when you pump 1,000 gallon minute water from the Coast Creek water Wellview, you stealing water outside your watershed. All right. So this is why my statement is partially true. It is a single water aquifer, but if you pump here, you influence your neighboring watershed. But I don't think you're going to influence the people in Tignish. Do you know what I mean?
I do.
So you have to be more precise.
Lynn?
Thank you, Chair. I appreciate that distinction. It makes more sense to me now how you are thinking of it in that way, and I think that's a really relevant point, particularly if we are measuring water extraction on a watershed by watershed basis. Those are not fully confined differences, are they?
That's
so
yes.
I could be managing my watershed. If it neighbored against Cory's watershed, I would still potentially impact him,
Yes.
even if I was measuring it on a very regional basis.
Absolutely, you should work together. Otherwise, when you pump, you're going to influence him, because the water is moving underneath the ground.
Lynn?
Thank you, Chair. I appreciate that. I didn't understand that difference previously, so that's actually really important. We've talked a lot about managing groundwater and extraction on a watershed by watershed basis, but we really have to recognize the interrelationship between...
That's an excellent point. This is a hydrogeologist. They should know that too. I like that you pick up this one really well.
Lynn?
Thank you, Chair. I appreciate that distinction, so that's helping me to understand this better. Thank you. You had spoken to models of extracting 5 inches of water from the, I believe it was the Wilmot River watershed that you were modeling on?
Yes, that's research cases.
And from that 5 inches of water, you saw a difference of 7% of recharge being influenced. Is that an accurate understanding of that?
That's correct, yeah.
Lynn?
Thank you, Chair. So as I understand it, for a crop like potatoes, you would be looking for 1 inch of water a week during the growing season. Is that I'm not sure you can speak to that, but that is certainly my understanding. And I'm just curious, an inch of water a week during the growing season, even if that was 8 weeks, it would be more like 8 inches of water. Do you have any idea of what sort of impact?
This one is a little bit, this is my new research, actually, is irrigation related. And the assumption is they use 1 inch of water for irrigation. But normally, that inch of water will last for a little while, because that inch of water top the soil to almost saturated to a high level of moisture. And then they will let it deplete to a certain level, because to the level that the crop will not suffering yet. And then they go back to pump. So it's not in 1 inch every week. So they have to take a break.
Lynn?
Thank you, Chair. Yes, I appreciate that, but I also think a factor in that would be the amount of soil organic matter that was in that soil, on how long it would retain that moisture for. How much exposed soil there was in a field would influence how long the water stayed in the soil. And also, I think climate change would factor into that, the daytime average temperatures, things like that. Is that a fair assumption? That
The soil organic matter one, yes, soil organic matter will increase the pores in the soil and increase the storage, but it's not significant. Then I have to say so. I have a curve, not here, but in my other presentation, and the correlation between water holding capacity and soil organic matter. It does increase a little bit, but not a whole lot. This first point I want to make. Okay, I don't think increase the organic matter. You can significantly increase the holding capacity. This is the first thing. The second one is, if you want the soil to hold the water, you have to have the water to hold. In a dry year, you don't have water to hold. So you have to put water there, let it hold. So it's the sources. You got to get the water sources for the organic to hold it. But again, I caution you, it's not increased dramatically. Okay.
Lynn?
Thank you, Chair. Yes, I absolutely agree. You can't hold water that's not there. I'm just trying to get a sense of how often a person would need to apply water to maintain approximately an inch of moisture in a week. Factoring in that low soil organic matter may result in that water depleting quicker. Climate change.
Actually, I have a manuscript submitted. It's about what you're talking about. If it's accepted, I can email it to you. It's about how much water you need to irrigate it and the economic implication too. Was that economically viable or not? So I did some research in COVID-19 and we submitted. It's under review. Those numbers will be available for you.
Lynn?
Thank you, Chair. I would definitely appreciate receiving that information. Thank you so much. One statement that you had made earlier, and then I will let someone else ask questions if other people have any, but then I'll get back on your list. But you spoke to the fact that even when we withdraw water, we may not see over the course of the year a significant impact to the aquifer, but you will see seasonal impacts to the aquifer. I'm wondering if you could just speak to that a little bit more. I want to have a clear understanding of this. We could have seasonal impacts to the aquifer that could very well recharge over the winter, but do we run risks of
depleting the aquifer? Okay. So when we say that we only use say 2 or 3% of recharge, and most of the remaining 95% recharge is going through the aquifer, is getting into the river. So on an average basis, and you're only using, even you're only using 30% of recharge, and that much, you're not going to deplete in the aquifer. But in the summer, the water can be very low. The water level can be very low. And your neighbor's well, if you pump a lot of right here, and your neighbor's well may be low, the water level may be low. His pump may be hanging in the air. But when the fall coming in, like this time of year, it's coming pump bounce back it again.
Lynn?
Thank you, Chair. I'm sorry, I know I said that I wouldn't ask any more questions, but that's just such an interesting point. So when we say we're using 2% or 3% or whatever percentage of recharge, we're talking about on average over the course of the year, we don't run the risk of depleting the aquifer, but that doesn't mean we don't run the risk of causing harm or detriment in the short term for...
It depends how you define the harm and determine the influence. You know what I mean? Depends how you depend it. Maybe if I have a well there, I don't use it, you make it dry, it's no problem. But if I use it every day, you make it dry, that's not acceptable. So depends how you depend. But you potentially, if you put your pumping well nearby your neighbor's well, you pump a lot of water, potentially you can influence that. But I believe when they issue the permit to you, they have to take that into account. At least they're saying that your pumping will no influence them. They will test that or model that and put a condition on you. So if you let people pump without any permission, that can potentially cause problem. But if you manage that, you may be in an acceptable level.
Lynn?
Thank you, Chair. So I also heard you say that when you withdraw groundwater from the aquifer, it does influence streams. And I feel like what you are saying is you really cannot pump without having some impact on a stream. And I feel like you're saying the impact isn't, how do you say this? The question is more political than it is scientific, isn't it? On whether or not that's an acceptable risk to the stream.
I think this is the question you answer. I cannot answer that question for you yet. It's a value. It's a value decision. Yeah. So what's acceptable, what's not acceptable, and there's no solid science to say that yet. That's what I can say.
I'll let someone else have a turn,
Sure.
Chair, and I'll come back on your list.
Sonny?
Thank you, Chair. Thank you very much for the presentations. Certainly enlightening. I got a couple areas I want to go. I really like your example of your bank account and the water. Like you got to have to put some back if you're going to be taking it out. Evaporation, like that, as much goes into the recharge as evaporates. Like, how do you come to that? Like, if it pouring rains and at night, it still evaporates?
There will be a little bit, I guess, but more in the daytime, the sun is shining, and then it's more related to temperature. Temperature dominates because evaporate need energy. At the nighttime, it's very dark. There's not much energy, sunshine, and to bring the water up. So at the nighttime will be very minimum, but mainly in the daytime.
And that's why I ask it, because like it's almost equal, right? 40%, 40%. So you think, it doesn't always just rain in the daytime, right?
Correct.
So I guess my other question is, okay, you talk about taking out and putting back. So there was a comment made at the last meeting I was here about maybe using some experimental wells and testing them. So be it government or be it private industry. What's your thoughts on that? Like, if they were done in a certain area, and I certainly appreciate what you said that, the watersheds can be affected greatly in one area, but not right across the province. So if there was wells dug to do irrigation and they were tested and monitored on a daily basis or hourly basis or what have you, what's your thoughts on that sort of thing?
I think you want the scientific data. So you need the scientific data. You got to do that to get the data. If you don't need the data, you believe in current science level. For example, currently we have the model can demonstrate this kind of level of accuracy. You can live with it. And for your decision making, I think you probably don't need that. But if you don't believe what the current science it is, you need more science to support your decision making. Probably you need to do that test. Do you know what I mean? So it depends on you. If you say, okay, I like your number, I have a full faith on your model, and we don't need additional data. We don't have money anymore. So So it's your own call. I mean, I actually and Michael Wannenhu, I think he gave a talk right here the other day, and he made a proposal for that research, and he put me on his team too. So I'm part of his team. If he got the money, he want me to look at the science for him, I will do that for him. I will be part of it. If he doesn't get approval. So as a scientist, we do the science.
Sonny?
So to your knowledge, so let's say we've done some science and you've done a great presentation here today. So it seems like the next step or the next possible step could be to dig a well or two and monitor them. How long would you have to monitor them? Would you think 1 year, 2 years, 3 years would give you a basis of where the aquifer is and the discharge and where you're at?
I think for his project, he's talking about a 4 or 3 years project, yeah. And he will, if you give the permission for him to drill those wells, and he will monitor him for so many years. And certainly you will improve the science because you got additional data. For science, more data will be better. And we have more, like I presented before, as uncertainty in models. And even nowadays, like the weather forecast is really good for short-term and forecast. They're still working on refining their model. They still be off sometimes, off chart. For example, they say today is sunny, maybe raining. They can be wrong. So there's uncertainty there. 90% of the time they're right. There's still 10% mistake. So those numbers will reduce the uncertainty of the modeling.
Sonny?
Thank you, Chair. And one more question. So in the essence of fairness, so if you were to do test wells, and maybe this is not a fair question to you, like, you know, you wouldn't want to have the lottery. You'd have to do it in certain areas where you would think that it could be tested and sustainable. Where would you suggest there would be some tests done if that was a road that somebody went down?
Well, for the test, I think there's so many factors from a science perspective. There's so many factors you have to take into account. You have to think about that representative the island, and you want to put the best bank of your money on it to get the best of science. You want to be to narrow down your uncertainty as much as you can. So I will use the science criteria to evaluate that. I will probably don't use a political thing like to evaluate that. So I would depend on where the data gap is. I will put it well there and get the best of the investment.
Thank you, Chair.
Steve?
Thank you, Chair. So we're talking a lot about modeling here. I heard you say that we'd need 20 wells to know what happens within an aquifer and watch them, but that's not realistic because it's too expensive, so we're going to do a few and use modeling. When Professor Van de Heuvel was in here speaking, he spoke about, we were talking about climate change, for instance, and modeling the effects that changing precipitation patterns might have upon the recharge rate here. And he was very much against using such models in this study because it might be better, it might be worse, so what's the point of using the model was, I believe, the answer. So when we're talking about using modeling for the groundwater levels that we have here, are we always erring on the side of caution when you have a model that shows it's going to be from this low to this high, or are we erring on the side of caution and using the lower numbers, or are we using the median?
As a scientist, when I present the numbers to the decision maker, I normally would have the worst case scenario and then average scenario, and then the promising, the optimistic scenario to them, and then I will let them make the decision. Which one? I think when they make decision, I believe then they will make put a factor of safety over there, and make that decision. And normally that's for science project and to use the data to guide a real world decision making, we normally put a factor of safety there. Because like you say, there's so many uncertainties out there.
Steve?
Thank you, Chair. So with regard to climate change, I mean, a lot of it is shifting water patterns, and the level of type of precipitation, the amount of precipitation we get are closely tied to it. So is there a difference between the recharge you'll get from the different types of precipitation that would fall upon Prince Edward Island's land?
I only look at the short-term data. For example, the 2000, 2001, I only look at what happened before. And I don't look at the projection in the future because, like you said, there's so many uncertainty there. And also, it's not my area. But I do hear that the province is doing the assessment how climate change influences recharge. I think before I came here, the province, I had a discussion with them. They will present a talk to you guys too. I think you will line up a talk. They will present a number to you how climate change influences recharge. Yeah, that's not my. I haven't touch on that subject yet.
Steve?
Thank you, Chair. So even more basic, I guess, does snowfall affect recharge different than rainfall?
Of course. And normally in the winter, the snowfall, and then it will, when it melt, it create recharge. If it doesn't melt, it stay on the ground. It will not create recharge. And the rainfall, it didn't go through the melt process. Rainfall is going to soak into the soil. But again, they are still H2O, still molecule of water. So eventually they will melt into the water format, liquid format. That's the part that getting into the recharge. And then the snowfall, the amount, of course, influence the amount of recharge, but it has to be melt in order to begin recharge.
Steve?
Thank you, Chair. I can't remember the watershed we were talking about, but 10% of water would reduce stream flow by about 40%. Was that Wilmot, was it? Or
That was the Walmart, and I have to correct you over there. And I say that if every potato rotation fields got irrigation, and then it's in a very dry year, that's the assumption, okay? It's in everyone got equal access to water, groundwater for irrigation. It's a very dry year, say 2001, and you use 10 inches of water for irrigation, and then you end up 40% of reduction in stream flow at that specific spot, and based on the model prediction. So that's the potential. That's basically it's kind of a worst case scenario.
Steve?
Thank you, Chair. So in that scenario, we're essentially using 100% of our recharge in that seasonality, and then dipping into our runoff numbers in order to get this extra 40% that the streams are dripping down by. Is that accurate?
So that's 40. I don't remember what my number. It's 40% of the recharge for the 440, but in that year it can be using about maybe a little bit more than 40%, maybe a little bit less than 40%. It depends on how much recharge that year will be. So do you know what I mean? But in the summer, there's not much recharge. You're using the recharge in the spring, storage in your bank account.
Steve? Yes, I understand that, but the 40%, that's not a reduction in the recharge rate for that year. That's how much the water level will go down in the streams and runoff? Is that what that number represents?
That's the stream flow reduction. But if you don't pump for irrigation, you don't pump that 10-inch water for irrigation, you're going to have this amount of flow over there. But if you pump 10-inch, everybody pump in that summer, and you're going to reduce flow down to 40% at that specific spot. So if you go down a little bit, maybe you reduce less because you are facing a big watershed. If you go up, you maybe reduce a little bit more. So do you know what I mean? So it depends on where your spots are. So you have to put the number in the context.
Steve?
Thank you, Chair. That's
Good for now. Lynne?
Thank you, Chair. I'm learning a lot during this presentation, so I do appreciate you taking the time to come in. Another question that I had is, I'm trying to get a sense of how long it takes for that melt to reach the aquifer. If you see melt happening in March, when can I expect that water to reach the aquifer?
Well, this is, okay, let me put it this way, okay? If you have the melt, for example, say in March, you have snow melt, and how long it takes that water to reach the water table? Okay, this is a very complicated question, I can tell you. And you know what? That from the ground surface to the water level, there's unsaturated zone there. And some people in our profession, we call it vadal zone. Vadal zone. So now let's make it simple. Unsaturated zone, can use this word. This unsaturated zone, what does that mean? It has three things over there: air and water and soil particles. Okay? So it has water there. So when you snow melt, that water has to go first into the soil in the unsaturated column. Even though you feel dry, but there's still water there. That storage has to go in down there. So if you melt 1 inch and that 1 inch seep into the soil, you're gonna spit out an inch from that unsaturated zone. You know what? Okay, what happened is the molecule from the snow melt will not be able to reach the water table in that season. But the molecule from a few years before is spit it out like a piston. All right, so in terms of water volume movement, it's gonna be almost like the same year. But it creates some problems for a lot of people, even for hydrogeologists. They think, well, we got a water table going up, and this year's snow melt reaching my water table. But no, chill. The chemicals this year is not gonna be reaching your water table this year. It's gonna take a couple of years, depends on how thick it is. You know what I mean? So that's very tricky, this one. Very, very tricky. This actually is I got a very good publication on this one, just recently in PEI.
Lynn?
Thank you, Chair. I'd be interested in seeing that publication. I would definitely like that. I expected that was going to be the case. So the water from this year, even though it will move water that's in that unsaturated zone itself, it does not reach the water table.
Correct. All the water reaches the water table. The amount equal to the amount you melt. But the molecule, the new molecule will not be able to reach the water table. It's only the older ones. So the one that on the line, like you're going to buy coffee in Tim Hortons. So the last one give a push and the first one got coffee. You are not going to get coffee. The same idea. It's like a piston. It's a pressure propagation.
Lynn?
Thank you, Chair. Say that term again. It's
Pressure transfer or pressure propagation.
yes. Thank you.
Lynn?
Thank you, Chair. Yes, that makes sense to me. I understand that. So the water is in the unsaturated space. When you have melt, it moves that water out of the unsaturated space into the water table. If you don't have the melt that year, or as much melt that year, that saturated space stays and doesn't change.
Correct.
But then in future years,
Yes.
so this is where we get our F.
Appreciate again and recharge again, replace. Just like a replace process.
Lynn?
Thank you, Chair. I understand that. I also have questions, like my colleague did, on how climate change will change that and impact that, but I completely appreciate you saying that's not the area that I've studied and I don't look at those models. It is my belief that in order for us to make decisions on this well, we need to understand that. I would like that to be part of what we as a committee consider when we are thinking about this, but I definitely understand that that's not something you're prepared to speak to, and I appreciate you just being forthright on that.
I think the province is doing that. Because I work with them quite closely, they update me what's going on, so I realized that they're looking at how climate change impacts the recharge. And actually, when they hire me to work in PEI, there's a few topics they want me to address. First one is the wellhead protection, delineate the wellhead protection zone, and the other one is looking at how pumping influence stream flow. And the third topic is nitrate. The fourth topic is climate change. So they hire me and to do those work. I haven't finished the climate change. I moved to another job, so I finished 3. The well field delineation, pumping impacts on stream flow, and the nitrate one.
Lynn?
Thank you, Chair. I know we have had Dr. Fennick in to speak to another committee, the Climate Change Committee, a number of times, and he had talked about how we are expecting to see more or less the same amount of precipitation in an average year, but that we can expect to see it come more often all at once with longer dry periods in between. And I think that has the potential to have a fairly significant impact on how much is actually absorbed and moving that old groundwater closer and closer to the aquifer. So I do think that's interesting, and I'm glad to know that the province is looking at this. Something that I've seen a number of times that I'm hoping you can help me understand, when I've read through the summary documents that are on the government's webpage for the Water Act, they speak about residence times, how long water is in an aquifer. Can you help me understand residence times a little more
Actually,
clearly?
those numbers come from me, from my publication. Yeah, I was involved in that research. We use two approach to do the age dating and residence time. And we use the treating. It's a isotope. It's a radiation isotope. And we also using a model to calculate that. So again, it depends on where you are. It depends on the residence time. It depends on what watershed and where you are. But on the average case, let's say using the Walmart as an example, which we have a lot of data over there, we find out that the aquifer, the shallow part, has only a few years residence time. So the water stay there for a few years, and then will be replaced by a new one. But if you go deeper, and from say of 20 to 40 meters that deep, it takes a long time for the water to go through. So the aquifer is in PI stratified, layered. Only the shallow part is very active. You go deeper, the age is older, and the rest are longer. So on average, the shallow part is a few years, and if you go deeper, it can be decades. If you go 100 meters deeper, it can be 100 years longer. Yeah. So that comes from modeling and from isotope dating. And also another student did follow-up work with in UMB, and his number are very consistent with my numbers too. So that's what we only say that, well, we have data. So if we don't have data on the other part, we can speculate it, but with more cautious on those.
Lynn?
Thank you, Chair. Yeah, I definitely understand that. I've read through both the summary document that's on the website and your original document, which the numbers do not match up with what the summary document says.
Is that right?
Yeah, I have quotes in front of me that I could speak to, but I'm trying to understand what the implications of that is. There is somewhere on the summary document where it says that at 100 meters of depth, it's at least 50 years old, but your research in the Wilmot River says at 100 meter depth, it is between 5,000 and 7,000 years old, which is not exactly.
Well, no. I don't think that I report that long number, but probably somebody else. Maybe it's a Daniel Paradise number.
It could
Yeah.
be.
So it depends on what methods you're using. So the
Lynn?
Sorry, thank you, Chair. I'm just wondering what the implications are of longer residence times.
okay.
Why does it matter if it's 50 years or 5,000 years?
Those are more important for the contamination remediation. So, for example, if you have pesticide in your water, if it stay longer, and many of the pesticide can degrade over time. Degrade, become a different breakdown.
Exactly.
So, but if you stay there very quick, the water goes very quick, and the toxicity and the parent compound can still be there, can be problem. So, do you know what I mean? And also, and if we want to recover our flush out the contaminants in the aquifer, our grandfather put in there because they don't know the problem. They put it fertilizer and then leach into the aquifer and it stores there for a long time. And if those things get into those deep aquifer, it takes a long time to flush out. So if you want to predict the water quality, you have to take in that residence time, or we call time lag into account. You can't assume that it's going into it and going out. It's not moving like what's happening in the river. It depends on how deep you are, and then it gives you anticipate water quality response improvement time. Do you know what I mean?
Lynn?
Thank you, Chair. Yeah, thank you for that. I believe I understand that. I feel like what we are saying is the water that has shorter residence times probably has higher levels of nitrates and pesticides when it comes back up.
Depends where you are. If you're under the crop lane, maybe. But if you're under the forest, there's no much nitrate pesticide.
Lynn?
Thank you, Chair. Yes, that makes sense to me. So, one final question that you had spoken to earlier was you had indicated that stream flow is about 65% made up of groundwater. That's higher than I realized.
In the summer, it's almost 100%. That's an annual average. In the summer, is no rainfall. Where does the water come from? It's from the groundwater. It's from your bank account, from your saving account.
Lynn?
Thank you, Chair. Yeah, that makes perfect sense. I suppose I made an assumption that there was a higher percentage of runoff and precipitation that made up river flow, but it's as reliant on groundwater as we are, certainly, if not more.
Only in the snow melt season, in the fall, in the winter, and snow melt season, you have pretty high runoff, and then in the river. But again, in that time, you still have a lot of groundwater in the river. But in the summer, you don't have snow melt, you don't have runoff, you still have water in your river, from the spring and from your saving account and from the aquifer.
Lynn?
Thank you, Chair. I've learned a lot from this presentation. I really appreciate you taking the time to come in. This has been very helpful. I'm just hoping you can answer one more thing for me, and then I will leave you alone. My last question, you had spoken earlier in one of your slides that if we were using that theoretical 5 inches of water, we would see a 7% use of recharge, and I'm wondering how long it would take for us to see those implications in the river. If I am pumping groundwater, when am I going to notice that I have made an impact? Do you know what I'm asking? I'm not saying that clearly.
That is a question that in our system, because our system is a fractured aquifer, and so again, going back to that pressure propagation issue. So if you pump here, and the river is over there, say 100 meters away, and you will have pretty quick response because the pressure propagation. But if it's gravel aquifer, the porous aquifer, it's not like fractured aquifer, and that influence can be a little bit later. So that part has to be assessed. I think currently, and based on our current parameters, and we put it in the model, it's a pretty quick response. Yeah, so that part should be, because that part should be, more research should be done on that one. So, and then we can determine the setback distance and those stuff. It is a factor, should be taken into account for assessment of the response of stream flow to pumping.
Lynn?
Thank you, Chair. Thank you for that. I understand what you're saying. It seems to me that in the same way that when precipitation lands on the soil, it takes quite some time before we see it make its way to the water table. I wonder if, even when we turn off a pump, how much longer we could see the river continue to drop. Do you know what I mean? Like,
yes.
How long does it
If you have only one well here, and that response may be a little bit longer, but you have multiple wells there, pump, and that interference, and that propagation, pressure propagation peak could be way faster and way more big. It depends on the volume you pump and the timing, those things, all those factors. But the aquifer in here does, based on my knowledge, it does respond quick.
Lynn?
Thank you, Chair. So that's good to know. If we turn on the tap, let's say, we will see an impact in a vulnerable stream pretty quickly. When we shut off the tap, what sort of impact can we expect to see?
It can respond pretty quick too, because when you reduce the pressure in here, and then it can build up, the pressure can build up pretty quick too. Things can come very quick and can go pretty quick. They follow the same physics. So that can be done by modeling. Again, can be done by modeling, and by small scale pumping test too.
Lynn?
Thank you, Chair. Do you have other people on your list?
I do, but that's
okay.
fine.
I'll be quick. Thank you. So I understand that it could fill back up relatively quickly, and I think over the course of a year, it sounds like it would average back out pretty quickly.
Yes.
But what about during the summer where you have those competition for water sort of moments? What about then? If you turn the tap off and there isn't new water coming into the system as recharge, are we sort of left with that until we see the recharge increase?
Yeah, that's a hydrogeology questions. They can use the model to simulate that, but I can tell you that what happened is, in the dry season you don't have recharge, okay? And then you take a volume of water out, and you create a cone, because Jordan cone over there. So you lower the water level a little, and then when the Jordan cone getting fill up, because the water nearby is going to fill up, and then you stop pumping, it's going to level, it cover up this Jordan cone, but then it's not going to recover to the same level before you pump it, because you only take a volume out. But again, because you fill in that cone and you build up the pressure again, you're going to increase the stream flow right away. But may not be to the same amount before you pump it, but it's going to going back quick too, because you fill in that cone very quick. That's very. You asked some really good questions.
A lot of them too. Lynn?
Not sure my colleagues are as enthusiastic about my questions, but I appreciate that. That makes a lot of sense to me. So, because water finds its own natural balance, when you pull the water out from the system, it will pull it in from neighboring watersheds.
It's going to recover really, really quick, but may not be to the same level anymore, because you only take out a volume.
Lynn?
Thank you, Chair. That makes a lot of sense to me.
Even though the recharge hasn't come yet, because the aquifer can adjust itself.
Finds its balance.
Yes, absolutely.
But would it have the potential to negatively impact another watershed while it's finding that balance?
It depends on how far away the watershed boundary it is. If you're far away from the watershed boundary, you have little impacts on them. But if you're right beside the watershed boundary, you probably, and those two wells are very close, one on this side of the watershed boundary, the other one on the other side, you can see each other, you're going to see the impacts there. Yeah.
Lynn?
Thank you, Chair. That's what I thought. This has been really informative. I can't tell you how much I've learned during this presentation, so I genuinely appreciate your time today.
Thank you very
Thank
much.
you. Sonny?
Thanks, Chair, and thanks again. I guess, so just for clarity on the presentation, so there's two aquifers, right? There's a shallow one and a deeper one.
They're the same, but they connect. So we, for statement, for description, we say there's a shallow part and a deep. Let's put it this way: shallow section and deep section is one aquifer.
Sonny?
And the deeper section is more pure water, but the shallow one could have some contaminants in it. Okay.
Depends where you are. Again, but if you're in the wood, and the shallow part is good too.
Sonny?
So I guess where I'm going with these questions, like we had someone in here from the Department of Agriculture that did a presentation and a statement that if you irrigate shortly after you put fertilizer on a plant, it'll absorb better than if you don't and you have a heavy rain and you have a runoff. What's your thoughts on that?
Okay, for the fertilizer, the rainfall and irrigation and how that influence the contamination movement. Okay, I think you're asking that. So I think I can answer these questions. At least I will try. Okay, so normally when they put fertilizer in the crop field, and they do it in the summer. Okay, in the summer normally don't have a lot of precipitation. And if there's sun, the water will normally land in the land and absorb in the soil, and then evaporate it back, or it transplant it back. We will not be able to create a net, a recharge, a drainage, and making recharge to water table. So normally we're not. But that in some cases it does happen. in very, very heavy rainfall that can leach out some fertilizer. But you know what? Fertilizer, a lot of people think that can be lost through runoff. But that's not very common unless you broadcasted it and have a heavy rainfall event. You create a lot of storm runoff. You can bring the fertilizer into the river. But normally they ban the fertilizer. They cut a change and cover it up. So when the rainfall comes, you create runoff. The runoff wash the topsoil a little bit, but the fertilizer is about 20 or 30 centimeters deep, so you're not going to be scrapped. The water will not be able to. So for irrigation, if you irrigation right and the crop grows really healthy, it needs more nutrient. So you improve the efficiency of nutrient uptake. That's kind of like a general science. Will that really happen very efficiently in the world? It depends on how you manage your system. There's so many factors have to take into account. In general, science say that. So irrigation improve the nutrient use efficiency.
Sonny?
If you do that right. But again, there's so many factors come into the equation.
Steve?
Thank you, Chair. I'd like to go back to all this talk of the pressure and rebalancing that you've been talking about. So during the dry season, if you do, the more pumping you do, the more pressure you'd build up and the faster everything would flow back to rebalancing. Is that accurate?
In the summer, and you pump groundwater, and then you create a drawdown cone there, you cannot avoid that, create a drawdown cone. And when you stop pumping, there's no recharge there, but there's a storage in your tank, in your aquifer tank. So that storage can rebalance. So the water, your well spot has a low pressure, even though you stop pumping, that low pressure spot still there, and then it's gonna pull water from nearby. So it's gonna fill in this drawdown cone level up. That water is coming from storage, from your nearby. It's not from recharge. If you have recharge in the summer, of course you help it recover quick. But I don't think that if you have recharge, they're gonna pump anymore because they don't want to waste money on fields. Do you know what I mean?
Steve?
Thank you, Chair. So once you've had a bunch of pumping happening and rebalancing occur, and your water table's now a little bit lower and sort of flattened out again, I guess you could call it. Yes. Then you have your recharge precipitation come. Does that affect how fast that recharge rate would add to that water table?
Back to Lynne's question, because the soil has water storage there, even though it's unsaturated, there's still a certain amount of water there. So it depends on the soil condition. If the soil is getting close to saturated condition, and you have rainfall, it's gonna be pushed down to the water table right away. But if the soil is very dry and you have rainfall, the rainfall will fill in the soil first before it can establish an effect pressure propagation to the water table. I hope you understand me. It depends on two conditions, okay? One is very saturated soil. You have rainfall, it's gonna squeeze out the water to the water table right away. And that pressure can be effectively transferred to push the water down to the water table. But if this soil is very dry, the rainfall come in, the first few events is going to fill in the soil first, and then you build up the pressure to push the water out. So wet soil, the precipitation can drive the recharge very quick. Dry soil, the precipitation cannot drive the recharge well. It takes a little while to get there. I hope you understand me.
Steve?
Thank you, Chair. Yes, I think I understand that. That's the drier the soil, the more it's going to absorb and whatnot. The question I'm wondering about is in that situation where we have saturated soil and it is making its way down and to contribute to recharge, when it's going down to a balanced water table, does it take longer to propagate down? Or, I guess one's lateral pressure as you use it and one's vertical pressure as the recharge comes. Is that a way for me to think about this?
This is actually, even the vertical zoom, and then the groundwater is horizontal moving, but they are the same system. There's only a water table in between, and then the soil is an unsaturated system, flow system, and then the aquifer is saturated system, but they couple together, they link together. So the pressure can be transferred to the aquifer quick. Even though if this is dry, and then it will be harder to transfer, but if it's saturated, very quick. Yeah, they connect. It's, pressure, you don't have the physical contact for pressure transfer.
Steve?
Thank you, Chair. Thank you for that answer. Changing gears a bit here. So when you've done modeling, you've done based on history when we had one dry year. Have you ever done modeling that would show the effects of multiple dry years, two or 10 years? If we had a long stretch of no rain, have you done those types of modeling?
You know what, this again is a very specialized questions. And why I pick the 1 year, because because in history there's no continuous dry back-to-back years for you to pick. There's no that window out there. Okay, that's first. But if you want to make one, so 2001 it was a dry year. Now, okay, let's put 2020 together with 2001 and see what happened. We have never seen that before. That can be a scenario. Modeling that doesn't cost very much money. You want to see that they can produce that. But what implications are for you, you have to, you take it. But I don't think that happened before. If that happened in the future, I can make one for you. But how realistic it will be, you ask yourself. The model certainly can do that. For example, 2020, almost over now. We got a rainfall data, we can put it into the model and put 2001 together. We'll see what happened. Well, that doesn't cost a lot of money. Will that have really good, realistic implication for you? I don't know, but there's no cost of much money to simulate that.
Steve?
Thank you, Chair. So what I'm hearing is it's very easy to do, but there'd be a lot of unknowns introduced into the modeling, calling into question the results. Is that what you're telling me?
How are you going to take the results to make your decision? What kind of implications are? But because that never happened before. So do you really want to put that into your decision making? You think this is going to happen? Or at least I should take that into account in your decision making. When you're giving water for people, and are you going to say, okay, 2002 dry and 2020, this 2 year back and back happened. So then you create problem for your neighbors. So I'm not going to give you water. So I think if you use that as a scenario to permit your water, probably people will buy into it because that never happened before. So you have to use a more realistic scenario to do decision making, in my opinion.
Steve?
Thank you, Chair. And I guess it goes back to what my colleague and myself have been talking about with climate change modeling and rainfall patterns shifting and the like. So we're going to get more rain and larger events in the summers is the forecast of the modeling, and less snow. And as I understood it, snow would contribute more to the recharge because it's going to saturate the ground and enter more often than rainfall is going to do. So in these situations, I mean, it's possible that those rainfall patterns would shift entirely differently than what the modeling might say, and we would have 2 years in a row of drought. So I would love to know what the implications of that are, so that when we're making our decisions, we can at least factor it in. So, yeah, it's fantastic.
The model can do that for you. And then I believe they have that's kind of worst case scenario precipitation distribution, and they may have 2 really dry year back to back in that scenario. They can create that to you. You can ask the province to do that. They're looking at how climate change impacts on recharge, and you can tell them that I want to see a scenario that have continuous dry year back to the back, and what impacts on the stream flow like in that scenario, and show me. And they can, I think they can do that for you. For me, I know working on this area anymore, but if I do, I don't think that's too hard to do it.
I'm sorry, I could,
Steve?
there's some noise there. I couldn't hear the last.
I don't think that to do this simulation, simulate this scenario is too hard. It's not that hard for model. But for a real world testing, it's very hard because you don't see that kind of dry year together. You're not going to be able to see that, but you can only do that in the models.
Steve?
Thank you, Chair. That's fine for now. Thank you.
Ola?
Thank you, Chair. I had a question about winter or spring recharge. Often I observe on PEI, I'm not a hydrologist, but you look at completely frozen field covered in ice and all kinds of water coming down. Would you have any recharge under those conditions? Wouldn't it all just run into the ditches and rivers?
Yeah, when the surface is frozen, and the recharge will be pretty hard to happen if you have a new rainfall event or new snowmelt event, and the ice lanes still in the soil will not be able to create effective recharge. That's for sure. But after they melt, their ice is melt, and then you have rainfall is going to create recharge.
Ola?
So my question was, are local, fairly minor climatic changes like that, does that have a big effect on the annual recharge, depending on what the spring is like? It varies quite a bit here.
Yes. And actually, I believe, for example, in the past 30 or 40 years, we have so many stream flow data, we have so many precipitation data, we also have temperature data. And we can certainly, I think they can certainly look at it and pick out the years, potentially have ice on the soil, and pick on those windows and see how what groundwater level respond to rainfall event, and how the stream flow respond to the event, to the period that has ice in the soil. They can certainly look at a specific scenario based on the past data. I think that those things can look at it. They can look at those numbers.
Ola?
Even though we don't have direct measurements to confirm if the soil is frozen or not, but they can look at it, air temperature, and figure that out.
Ola?
I was really interested in your modeling of irrigation. You used two models, one using 5 inches of water, one using 10 inches. Wouldn't you use the highest one? Because really what you want to irrigate is to protect yourself against dry seasons. So is that not the model we should be using?
I do show you the high one there. So I have the 5 inch, 8 inch, and then 10 inch there. But when I compare the two watersheds, Woma and Winter River, I only took the 5 inch one. But the 10 inch impacts is on my graph. It's in one slide.
Ola?
I think you mentioned that the 10 inch resulted in a 40% drop in the stream flow, something of that sort.
The 5 inches is
Yeah.
only 10%. Almost linear.
Does that include the seasonal effect of a dry season as well? That would drop the stream flow?
In the dry season, the dry year. That happen in the dry season. It actually is kind of like the worst case scenario.
Ola?
So that means, I was wondering what those numbers are based on. Surely it's not irrigating every single field in the watershed. Is it like a certain percentage of the fields?
What I did is, at that time, those numbers was done in 2003, 17 years ago, when I worked with province. So I borrowed their numbers officially, technically. And what we did is, we look at a land use map, okay? And then we say that one high capacity well can supply water for 80 acres, okay? So then we calculate over all acreage, land there need water every year. And then we use in a circle, like a pencil cap circle, and we put an ink over there, and we put this is 80 acre circle. So we put one here, one here, one here, one here, and then we see how many we can get. Then we use, because it's a 3-year rotation, then we say, okay, 3 circles using only 1 well. Then we created, based on that 2003 land use data, you need to say 20 or 23. I forgot about how many wells you need to irrigate. So then we count how many wells we need. So that's how we came out with. I still have my research note on the binder somewhere. Still have those circles on the map there. So I worked with George and Jamie on this. Jamie was the hydrogeologist by then, 3 of us.
Ola?
Okay, thank you, Chair.
You good?
Yeah.
Lynn, for our final, possibly 2 questions?
Thank you, Chair. I'll try to make this brief, but something my colleague was asking you about spurred another question in my mind. We have been using 2001 as a model because it was one of the driest years next to this year. But something that you said about how unsaturated soil holds water and then moves it down makes me wonder what the implications would be with the last, say, 5 years in PEI's context, because 2015 certainly wasn't as extreme as 2001, but it was considered a hot, dry summer, and so was 2017, and so was 2020. And it seems to me that the cumulative effect of multiple
Yes, dry year.
dry years, even if they're not extreme dry like 2001, could almost have greater implications for the water table based on what you've just explained to me about how water moves down. Is that accurate? And can you speak to that a little
I think we need to do the assessment before we can say so. And I'm using the data from the data I did it in 2003. That was many years, almost 2 decades now. You can, if you decision making, you need that information. I think you can push the province. They can use the latest windows, a 5 or 6 or whatever, and to do the simulation for you to demonstrate to you and present it here. I think they can do that. And then they hire somebody to replace me, and then they can do that for you.
Lynn?
Thank you, Chair. Thank you. I really appreciate that. And my last part on the same topic, how many years of data would you think would be a useful model for us to be asking for? I think that in the last little while, we've seen quite a dramatic change in hot, dry, even if it's not the extreme hot, dry of 2001. And I wonder how many years back we should have modeled collectively to give us a sense of what we're looking at currently, for it to be meaningful.
Actually, in 2003, when we built the model, we just using ready available data. We didn't do a specific collecting data. So why did we do that? And I think the key thing I was mentioning in the beginning of my talk is we are very lucky in PEI. We have a quite uniform geology. So if you're in Ontario or in Manitoba, you want to build a model, you have to spend a lot of money to look at the geology, because you cannot make an assumption this is going to be sandstone aquifer there. But in here, if you say that, I say this is sandstone aquifer in here, I'm going to put this in my model, and you come to challenge me, okay, let's bid. I can bid you it's going to be like that. Do you know what I mean? But in there, they don't. So then you're asking me how many years data you need. So, but then we didn't spend a lot of money on crystallizing the geology, and we have some Environment Canada's long-term hydrometric station data, stream flow numbers, and we have land use, and we have soil map. We put those things together, and we can do a pretty good job by then. But again, today we can still use a similar approach to put those 5-year windows in your model. But if you have real-world data, like from the Coast Creek, I think you have more faith on the results, better than the number I present today, if we really do that.
Lynn?
Thank you, Chip. That's the end of my questions. That's really helpful. I appreciate your time so much today.
That's
One last quick
one last question, Steve?
One last quick one. I thought I recalled reading somewhere, and this is just a high-level question. I'm not sure how accurate this was or not, but it seemed to indicate that if you took from the runoff, you might affect the recharge rate itself, like if you were directly taking from the streams instead of taking from groundwater. Is there a relationship that goes back the other way like that?
when you have rainfall and the rainfall fall to the ground surface, if the soil is not saturated, it's going to saturate first, and it's going to create recharge actually first, and then will be the runoff. So if you take off the runoff, you're not going to influence your recharge very much. That's what happened. So they're two separate pathway of the flow of the precipitation.
Good. All right. Well, thank you very much for your time today and for coming in and answering everyone's questions. It's very much appreciated.
Thank you.
We're just going to recess for a moment and while you pack up, and then we'll continue with our meeting.
Okay. Thank you so much. Thank you so much for meeting.
Okay, on to new business. Do we have any new business? Hal?
Just a question, an ask basically. So last week during the presentation, you referred to or read from some emails in your presentation, in your line of questioning, and I asked if we could, or I put a motion forward actually, if we could have a copy of those emails. And it was, you asked the clerk for direction, and then you agreed that you would circulate those emails. I haven't received them yet.
Clerk?
So actually the original request was technically just from member to member. So it was left up to the chair if you wanted to provide them or not. If it was a decision of the whole committee, however, that would be, you could make a motion, I suppose.
Hal?
So Chair, you agreed that you would send them out last week.
I can't recall. Did I?
I said that I could distribute them to the committee if that was the wish. He did say sure, but yeah.
I would prefer not to protect that individual's name. Hal?
Well, Chair, so you also received...
Unless you want them redacted, with the names redacted, you can have that.
You also received an email from Venerable Yvonne on that evening, stating that she went to, because in that particular line of questioning you used, you spoke of Venerable Janet. That was where the emails were being back and forth from. So so Yvonne went back and asked Janet if she could search keywords to try to find those emails and correspondence so that they could have full transparency. They couldn't find that. So they sent a request to you asking for a little bit more clarity on it for the purpose of full transparency. Did you respond to her?
No, I think I've discussed this with the clerk. No, I haven't gotten back to her yet.
Okay. Will you be getting back to her?
I'm not sure.
So
I'm not sure what you're looking for
Okay.
exactly.
Well, no, 'cause so basically-
I'll give you the emails, Hal, if you want.
No.
the emails.
But basically what she's, and I have a copy of the email.
Yeah.
So basically what she was asking, she couldn't find any emails that you referred to by doing a search in the keywords.
So you're saying the emails aren't real?
So she wanted to get a date and subject lines that were written in the emails so that they could get that copy.
Yes.
So they could provide full transparency.
Yes.
So if you're gonna, you had mentioned in emails that it was in correspondence with Venerable Janet, so they cannot find those emails, and they would like to have those, find those emails, right? Just, I guess, again, I keep going back for transparency. So I don't understand why you won't get back to her, it's been a week, or you won't provide the copy of those emails that you referred to the House if there's no problem with them, you know?
I don't have an issue as long as I can redact the names.
Okay, so basically then I'll put a motion forward asking that you provide the committee and also the GWBI with the dates and subject lines that were in question during your addressing questions to them last year and your expression of concern, and provide the committee with the emails that you used in your line of questioning. So I'll put that motion forward.
Can you read that? Do you have that?
So provide the committee and GWBI with the dates and subject lines in the emails, and provide the committee with the emails as well. And are those emails, do you want them to be committee documents, or are we looking for them to be publicized? Not publicized, but available to the public if they were to ask the committee member to provide.
They were asked, there was questioned in a public forum and read out in a public forum, so I would assume that we would agree on it being public.
Sure. Yeah, it'd probably be good to have public that people were circumventing the Lands Protection Act. I'd have no issue with that. Yeah.
Agreement of the whole committee?
Yeah. Well, it was certainly in an email. Yeah.
So,
Which I have every right to read out in the committee. So.
okay, and you also
Yeah.
have every right to read out. If you're sent emails as a chair, then that's why I'm asking this. So they should be shared with the committee.
Okay, yes, if you're making that motion.
Yeah.
Yeah.
So the motion, I put the motion forward.
Okay. All in favor? Aye.
Aye.
All right, motion carried. Any further new business? No? Motion to adjourn? Sonny, thank you.